So we're going to talk a little bit about the kinetics of nuclear processes. Now the good news is all nuclear processes are first order kinetics. All of them. Positron emission, beta decay, alpha decay, gamma emission, electron capture. They're all first order processes. Now if you want to look, if you've got your book on page 972, there is a chart of the transuranium elements. I mentioned this process in a previous video, and it takes you through the process of going from uranium all the way to lead-206. I think I may have said lead-208 in the previous video. Lead-206 is the biggest stable isotope in the periodic table. And that's why it's the ending point for the transuranium process. Now we'll deal with a lot of our examples come from those elements because they've been very well characterized and they come in a series of steps. Some of the smaller elements have just a single process that it goes through in order to get to become stable. But when we think about the kinetics of nuclear reactions, again, first order. That means that the rate equals K, our rate constant, times N. Nuclear chemists and nuclear physicists use N for number of atoms. A lot of times they deal with atom counts. And so instead of concentration of A at time 0 and time T, we have N and N0 for these processes. So the rate law for kinetic processes is usually written as K times N. First order integrated rate law, thinking all the way back to that chapter, means that the natural log over N of N over N0 equals minus KT. Again, we're using N's instead of A's like we did in class before. So this is at a later time. The subscript 0 is for the original time. Equals minus KT. So remember, for this one, first order, we had a plot that looked like this. Linear plot. Slope equals minus K. And for this one, it was the natural log of N versus time. And the y-intercept is the natural log of N0. So we can plug in to this kind of equation with concentrations, molarities here. We can plug in with numbers of atoms. 10,000 atoms up here, 20,000 atoms here. That works. We can also plug in percentages. Now you're going to see between the homework and exam and probably on some quizzes and things like that, something like N over N0 is 20%. And what that really means is that the ratio N over N0 is actually equal to 0.20. The percentage as a decimal. Okay? So if you see a problem, and write this down, make sure you write this part down, or remember it, or both, better yet. If you see a problem where it says that the current radioactivity for a material is 20% that of living material, or 20% of the original, that means N over N0 is 0.2, the 20% converted into a decimal. So if a problem says that the current radioactivity of this material is 35% of living material, this is 0.35. And you solve all of this just knowing that ratio. This is a 0.35 there, or in this case a 0.2. Okay? It's important to know what those mean because these problems are presented to you a lot of times differently than the original kinetics problems were back in that chapter. So again, N equals molarity of solution, or number of atoms. It can even be grams of atoms, because we'll have grams and grams. It's the same material, so there's no stoichiometry that has to go on here. So you can even use 10 grams up top, 12 grams on the bottom. That'll still work, okay? Because that's directly proportional to the number of atoms. And also keep in mind what this percentage means. 20% means N over N0 is 0.2, okay? Now for this process, the half-life was the other equation we need to throw in here with all of these. .693 over K. Half-lives vary greatly from one isotope to another based on how relatively stable or unstable it is. Shorter half-life means less stable. Long half-life means that it's a more stable isotope. So these sorts of processes, the fact that it's a well-established first-order set of kinetics, allows us to do calculations to predict how much material will be left after a certain amount of time, or if we know right now how much there is, how much there was a long time ago. So that's the basis for radioisotopic dating. Carbon-14 dating is the one you hear about most often because that deals with living, breathing, or plant material type organisms. So carbon dating utilizes this reaction that occurs in the atmosphere. An average nitrogen-14 atom, a typical nitrogen-14 atom, collides with a neutron, which happens more than you think, especially in space where there's no atmosphere or very little atmosphere to protect it. And when a nitrogen collides with a neutron, we get carbon-14 and a hydrogen atom. Now, in the atmosphere, the carbon-14 concentration is relatively constant over a long period of time. And so if we know how much carbon-14 a living being has in its system, and we dig up a relic or plant material, you dig down in the soil, dig up some plant material, and carbon date it, what we're doing is we're finding out what was N0 for that. We're going to calculate what it is now, and we know what N0 is because we know what living material has, so we're using that to calculate time. How long has it been since that animal or plant breathed its last? Now there are some things that we have to keep in mind as we do carbon dating. The equations work great. There's nothing wrong with the kinetics equations. Natural log of N over N0 equals minus KT works. But we do have to take some of this with a grain of salt, because what we're presuming is that over time, the concentration of carbon-14 in the atmosphere has not changed. That carbon-14 generated in the upper atmosphere filters its way down into the plant materials and then back up the food chain through whatever eats those plants and then whatever eats those animals. So it's presumed that the carbon-14 content in all living material is the same and has been for a long, long time. Now we know for a fact that our atmosphere is changing. Okay? Climate change is occurring. So we kind of have to take these carbon dating dates with a little bit of grain of salt. So if you're ever watching a Discovery Channel show or History Channel show and they say they sent something off for carbon dating and it came back to be 32,743 years old, they're not that good, okay? Best you can do is probably plus or minus 500 years or 1,000. So if something comes back as 32,000 years old, that's fine. But 32,473 years is a little bit too eager on their sig figs. So we come back to the next video, we're going to start looking at some of these kinetics problems and calculating some answers. Okay? Be right back.